Hello, I'm Phoebe, and today I'm going to be teaching you about Sierpinski and fractals. First, we're going to talk about Sierpinski's gasket. Now, Sierpinski's gasket has existed for a long time. There's evidence of the pattern dating all the way back to 13th century stonework. However, it was not until 1915 when Polish mathematician Wacław Sierpinski formally described it. Sierpinski's gasket is made up of fractals, which are mathematical sets usually obtained through recursion, which is basically just repeating a process over and over. Below is a Sierpinski's gasket I made. To make one of these, you can take an equilateral triangle, then find the midpoint of each side. From there, you are going to draw a line between each of those midpoints, creating a triangle in the middle. And with that triangle, you're going to remove it from the hole. This process is repeated over and over again, as you can see through recursion, taking away more and more triangles, however, creating more and more smaller triangles. These triangles have self-similarity, which means each resulting shape up close looks essentially the same as the whole. So as you can see above, we used recursion to make a fractal, and this fractal has a specific name, Sierpinski's gasket. Next, we're going to talk about area. Now, how would you calculate the area of each stage of this triangle? It's rather simple if we imagine that each side is equal to 1. By making a midpoint, we're cutting that line in half, and now it equals 2 sides, which are equal to 1/2. Every time we do this, cutting the triangle into smaller parts, we take away 1/4 of what was remaining in that last stage. This makes the equation exponential, because as we keep moving forward, we keep taking away 1/4 of what was left before. Another way you could say this is you're timesing 3/4 what the area was in the previous stage. So it doesn't get harder while we reach higher and higher stages. We can use the explicit formula 3/4 to the power of n, with n representing our number of stages, to help us find the area left over. However, that was just to calculate the area that was left over. If you wanted to calculate the area that was removed during each step, we would have to use a different formula. Since we know that each newly formed triangle is equal to 1/4 of the area of the triangle it came from, we can use a formula like the one below to find out what the area of each individual triangle produced will be. Now, how does that relate to the area of the removed triangle? Well, if you think of it, each triangle that's removed is equal to the other triangles in its stage. So if we know how much an individual triangle that is formed equals, then we also know how much an individual triangle that is removed equals. For example, let's use stage 1. If we put 1 in the place of n, then 1/4 to the power of 1 is just 1/4. So we know that each of the triangles formed in stage 1 is equal to 1/4 in its area. Now, because of that, we know that the triangle that is removed has to also equal 1/4. So, how do we find out the amount of triangles that is removed during each stage? Well, there's another formula for that. That formula would be 3 to the power of n minus 1. Now, this formula obviously doesn't work for stage 0 because nothing is being removed in stage 0. However, if we take stage 1 for example, if we put 1 in the place of n, that's 1 minus 1 equals 0. Then 3 to the power of 0 equals 1. That would mean that one of our triangles that is equal to a quarter in area is going to be removed in stage 1, which would leave us with free triangles equal to 1/4 or 3/4 of the original triangle. Now, we can continue to use these formulas for the stages after. For example, let's look at stage 2. If we put 2 in the place of n, then that would equal 1/4 to the power of 2, which is basically 1/4 times 1/4. If you do the math for that, it comes out to 1/16, because 4 times 4 is 16, and 1 times 1 is 1. Because of this, we know that each triangle made in stage 2 is going to be equal to an area of 1/16, if we keep in mind that stage 0 is equal to the area of 1. Now, with stage 2, we can calculate how many triangles are going to be removed. So, we take 2 and place it in the place of n. 2 minus 1 is 1. 3 to the power of 1 is 3. So we know that 3 triangles with the area of 1/16 are going to be removed. Otherwise, you could say 3/16 of the area of the triangle is going to be removed in stage 2. Now, using these formulas, I filled out this chart here, and as you can see, the triangle's area in total is getting smaller and smaller and smaller, as well as the area of the total removed triangle. Now, we already have a formula to calculate the area that is left. It was 3/4 to the power of n. Now keep in mind this formula doesn't work for stage 0, however, we assume that stage 0 is 1 to begin with. However, if you want to do it the old-fashioned way, look at stage 1 and the area that is left. 3/4 of the triangle is left after stage 1. But in stage 2, 3/16 of the original triangle is being removed. Now, how do we calculate the area left? Well, we can take 3/4, and to make the denominators equal, we would times both the denominator and the numerator by 4. This would leave us with an area of 12/16. Now, we know that 3/16 are being removed in stage 2. So if we take 12 and take away 3 from that 12, we get 9, leaving us with 9/16 of an area left. So both the formula and doing it the old-fashioned way works. Now, theoretically, this gasket could go on forever. So what does the area equal after an infinite amount of stages? Well, it basically equals 0. Since the area of the gasket is exponentially shrinking, it is forever nearing 0, and at a point, the number of zeros after the decimal place will just be so large that it's unnecessary to calculate, because it's accepted as being just 0. This also goes for any positive fraction less than 1 that is set to the power of infinity. Since the fraction is exponentially going towards 0, after an infinite number of times, it just keeps going towards 0. So we accept it as being 0. Next, I'm going to tell you about the chaos game. The chaos game is basically a game you can play to make fractals. You can actually even make a Sierpinski's gasket through the chaos game, and that's what I'm going to be telling you about. To do this, we're going to place 3 vertices for a triangle, and then you're going to place a dot somewhere inside that triangle. This is called your seed. From there, you're going to roll a die for one of the 3 vertices of the triangle. Then, find the midpoint between your seed and the vertice that you rolled, and place a point there. And then you continue this process. From that point, you're going to roll for one of the 3 vertices, and then plot the midpoint between those two vertices. You might be telling yourself, well, this doesn't look like Sierpinski's gasket. What is this? Well, that's because you have to play multiple stages to actually see the fractals form. For example, after 50 rolls, you can hardly see it, but you can kind of see that a triangle is starting to form, right? Then, after 500 rolls, you can actually start to see the Sierpinski triangle forming. After 5,000, it becomes much more obvious. Now, a Sierpinski's triangle doesn't always have to be perfectly aligned like an equilateral triangle. For example, there's this thing called twisted Sierpinskis, where you can skew the corner points of each triangle that is made after each stage, and it creates this sort of twisted, I guess is a good word, triangle. These twisted Sierpinskis are often used to create mountain-like shapes, for example. Now, Sierpinski's curve, or Sierpinski's arrowhead curve, is another way to construct a Sierpinski's gasket. You can achieve this generation by starting with a large curve, as you see in the image, then replacing each segment of this curve with 3 shorter segments, forming 120-degree angles at each connection between 2 consecutive segments, with the first and last segments of the curve either parallel to the original line segment or forming a 60-degree angle with it. So let me simplify it. Basically, each of these segments in the curve is going to become a curve of itself. And then with that process repeated, it ultimately makes a Sierpinski's gasket type shape. Now I'm going to move on to fractals. Here are some helpful definitions as we move into fractals. Initiators are the starting shape or line in our fractal generation, i.e. stage 0 of a Sierpinski, which is just your triangle, or you can even think of what we looked at last slide, the curve would be your initiator. Now, generators are the additive or subtractive changes made to create fractal generations. For example, in Sierpinski's gasket, it would be the removal of that middle triangle in each triangle. Now finally, it will be helpful to know iterations, which are the stages of fractal generation. So if you think in Sierpinski, we just called them stages. Those are iterations. Now, fractals aren't exclusive to Sierpinski. There's just about an infinite amount of fractals that can exist. For example, below, I put in the Koch curve, which is another famous fractal generation. As you can see below, you take your generator and add it onto each segment of your initiator. This creates another iteration. Here's another example. This fractal replicates a tree, and your initiator is just a line segment, with your generator being a Y. As you can see, for each iteration, we add on one of these Ys, or this generator, to the end of each generator before it. And as you can see by our final shape, it looks a lot like a tree. Now, it kind of is really symmetrical, and that's where randomness can come in. For example, you can decide to skip some generations here or there so that it kind of looks more random and looks more natural, like you would see with a real life tree. Now, one of the cool things about fractals, which I love about them, is that you can find them basically anywhere in nature. For example, as you can see below, there's a seashell or a river basin where it splits off into all these little pieces. And you can also see a lung, which grows in a fractal formation, and I think that's just really crazy. That's inside us. Now, there's not necessarily one known reason for fractals to exist in nature, but one of the common theories is that they exist to take up more space. For example, if you were a fern, you would want to use fractals so that you can create more space to take up more sunlight. Or if you're lightning, for example, which we're going to see on another slide, it breaks off into fractals looking for places of the least resistance. Here are some more examples of fractals that can be found naturally. For example, lightning and ferns, as I talked about on the last slide, trees, like I talked about 2 slides ago, and even snowflakes as well. Here you can see leaves, mountain formations, a peacock's feathers, ammonite, even broccoli. Well, technically this is a special type of broccoli, but even if you look at the broccoli you find in the grocery store, it sort of has fractal generation as well. Thank you for listening.